Hello everyone. Today we're going to be analyzing the motion of a sleeping top. We'll start off by representing the top with a cone spinning on its tip. This is a decent approximation because the cone spins along its symmetry axis at a fixed point, much like the sleeping top does. This cone has a mass of m, a height of h, and a base radius of r. To help us describe the motion of our top, we have a question in mind. For some arbitrary angular velocity, omega, what is the angular momentum L? Let's initialize a coordinate system. Cylindrical coordinates work best here and make the calculations easier to do compared to a Cartesian system. We need to find the inertia tensor in order to calculate the angular momentum. The inertia tensor is a 3x3 matrix made up of moments of inertia from a rigid body. Multiply the matrix by a certain angular velocity vector and out comes the angular momentum. For the case of our sleeping top, the symmetry about the E3 axis simplifies our inertia tensor to the following diagonal matrix. If we multiply the angular velocity vector to this matrix, we get the principal moments multiplied to their corresponding angular velocities. It is important to note that if the angular velocity vector points along, say, the E3 axis, the angular momentum will also point in that direction, while the angular momentum components along the other axes will be zero. This brings us to the topic of principal axes.
For any rigid body rotating around a fixed point, there exists three principal axes. For a top, the axis of symmetry along the length of the cone is one principal axis. Any two axes pointing perpendicular to the symmetry axis are also principal axes. Again, the important property here is that omega points in the same direction as L along these axes. Now we can use all this information to find the motion of the cone when gravity is involved. Angular momentum is equal to the inertia tensor multiplied by the omega vector, and the change in momentum is the torque. The torque acting upon the cone will be R cross F, where F is the force of gravity. From the cross product, we see that the direction of torque is perpendicular to the E3 axis, meaning that the torque is into the page for our diagram. This causes the top to spin around the z-axis at a constant angular velocity. The direction of angular momentum will change, but its magnitude will not. We call this phenomenon precession. Another way to express torque is to equate the change in angular momentum with r cross mg. And if we rearrange for change in the E3 axis, we get the following. We can see that change in E3 is inversely proportional to the angular velocity term. So as the angular velocity of the sleeping top decreases with time, the change in E3 increases. Near the end of its spin time, the angle that E3 axis makes with the z-axis will drastically increase, as can be seen in the video. Precession will continue, but at a much larger angle.
Come on.